Okay, so yesterday we were trying to finish up on chapter 2, okay? So in chapter 2, we mainly talk about how to use an impulse response to characterize a linear time-invariant system, right? So if you can use an impulse response to characterize a linear time-invariant system, this means that various properties of the system should be reflected in the shape of this, or the form of this impulse response. Right, so we looked at cases including, a system with or without memory, invertibility, causality, and so on. Okay. So at the end, we went back and sort of reviewed what it means to view a impulse function, right? This delta of t here, as a limiting form or an idealization of a pulse that is short enough, okay? So previously, when we first introduced the unit impulse function, we described it as a limiting form of this short pulse, delta sub capital delta of t, which is a pulse of this rectangular shape, okay? So as capital delta goes to 0, this magnitude blows up to infinity, and therefore it behaves as this unit impulse that we define. Okay. But yesterday we showed, right, through this sifting property here, that actually there can be many different forms of these short pulses that all have a limiting form behaving like the unit impulse. Okay. So the way we construct it is, by taking, for example, right, suppose we start out with this rectangular short pulse here, right, by the sifting property, if we take the convolution of this rectangular pulse, we get another pulse, r sub delta of t, that is in triangular form, but still, as capital delta goes to infinity, it converges to this delta of t. So following this similar reasoning, right, you can construct an unlimited number of short pulses that behave like delta of t in the limit. Right? You can do this by taking, again, let's say the convolution of r in itself, or r and delta, or the convolution of any short pulses of this type that is produced from this operation. Okay. Now, what's important is not really how we constructed these short pulses. Right? This discussion is to tell you that there are unlimited number of short pulses that, in the limit, behaves like this delta of t. Now, so what this tells us is that if you want to define delta of t as a limit of some function, this definition is really not unique or consistent. Okay. But this is really not, our primary concern, right? When we define an impulse response, we're not primarily concerned with what the values of delta is at different time instants. What we're really concerned with is how it behaves when passed through a system, okay, and how the response to the system approximates the response of other pulses that are short enough. Okay? And we can see this through this example here. Right? So in this example, right, these are responses to differently shaped short pulses. Now in this example, you can see that the response that you get from the unit impulse well approximates the response to all these differently shaped impulses, differently shaped short pulses, as long as this delta, right, the duration of the pulses, is short enough. Okay? So therefore, it's sufficient for us to focus on studying the response to this unit impulse, right, instead of having to specify each time the exact shape of the pulse that we're looking at. Okay, so this gives us some convenience or tractability in our studies. Okay? So the main purpose of defining the impulse, unit impulse, is to help us study or characterize the system in terms of the response to this impulse. Okay? So in that sense, instead of defining the unit impulse by the values over time, right, the values that this function takes at each realization of t, we instead, it's actually sufficient to just provide delta of t with this following operational definition here. Okay? So what really concerns us is, right, well, like we just mentioned, right, what really concerns us is how this delta of t behaves when passed through a system. And we know that the behavior, right, is characterized by the convolution of delta of t and, let's say, this response to the system or to any particular signal that we're looking at. Okay? So what really concerns us is how delta of t behaves through a convolutional operation. So we can define delta of t with this operational definition where whenever you take the convolution between delta of t and any other signal, it will return back the same signal again. Okay? So you can define delta of t as a function such that whenever you take a signal convolved with delta of t, you'll get back the original signal again. Okay? And you can show that all of the properties that we previously showed for a delta function can be proved using this operational definition. Okay. So here we give two examples. One is the unit area property, right? We previously showed that the integral of a unit impulse should be equal to 1. Okay? Now, how do you show this property from this operational definition? Right. So you can do this by simply taking the case where x of t is just equal to a constant 1. So we take the case where x of t is equal to 1. So if you plug this inside, right, the left-hand side is 1. The right-hand side, right, which is the convolution, is the integral of delta of tau x of t minus tau d tau. And x of t minus tau here is equal to 1. Okay? So this integral becomes the integral of delta of tau d tau from minus infinity to infinity. Okay? So this shows that with this operational definition, it is sufficient to prove the unit area property of the unit impulse, right? Namely, the fact that the integral of the delta function should be equal to 1. Okay. Now, we can also use this definition to show the sampling property, which tells us that if you take the integral of any signal g and delta, okay. So suppose that g is any signal, right? If you take the integral of g times delta, right, a unit impulse at time 0, then it will sample out the value of g at time 0. Okay? So this is a sampling property of the unit impulse we showed before. Okay? Now you can show this. Okay, you can show this also using the operational definition. And you do this by taking x of t as g of minus t. Okay? So suppose you substitute this into the definition above, then g of minus t is g of minus t convolved with delta of t, which is the integral of g of tau minus t and delta of tau d tau. Okay? So originally the convolution of a function g of t and delta of t would be the integral of delta of tau and g of t minus tau. Okay? But since there is a minus sign here, this should be tau minus t instead of t minus tau. All right? And then just by choosing t equal to 0, right, we have on the left-hand side g of 0 and the right-hand side g of tau times delta of tau integrated. Okay, so by choosing t equal to 0, we have g of 0 equal to the integral of g of tau delta of tau d tau. So this delta function, or the unit impulse, right, is just a special example of a larger class of so-called singularity functions that you can define using similar operational meanings. Okay? Now this one is of most importance to us, okay? But there are also other kinds of singularity functions that you can define using operational definitions through a convolutional operation. Okay. So I don't want to go through the details of this, but we could just probably give an idea of what these functions could be, right? So like I just mentioned, this unit impulse, right, is a special case of so-called singularity functions that are defined operationally by their behavior under the convolution. Okay? So the unit impulse is defined under the convolution as a function that satisfies this equation here. Okay. Now we can also define something called the unit doublet, denoted by u sub 1 of t, as the derivative of the unit impulse, or in other words, the unit impulse response to a system that looks like this, right? Because if you have a system where the input-output relation is given by this, right, y of t is equal to the derivative of x of t, then the impulse response of the system, right, the impulse response is the response to the impulse, right? So the impulse response of this system can be obtained by substituting x of t equal to delta of t inside, and therefore the response is exactly the derivative of delta t. Okay? So if you define u sub 1 of t, right, as the derivative of a unit impulse, then you can also view it as the impulse response to a system like this. So the operational definition of this unit doublet is a function u sub 1 of t such that when convolved with a signal, right, meaning that if you input any signal x of t into this system, your output would be the derivative. Okay? Now you can do that, you can do that for many different cases, right? So this is another example, right? You can define this u sub 2 of t as the second derivative of the unit impulse, or equivalently, the impulse response of a system y of t equal to the second derivative of x of t, right? So again, the reason I can say this is because the impulse response of this system is obtained when you substitute delta of t inside here, and therefore the response is just the second derivative of delta of t. Okay? So therefore, this u sub 2 of t is, right, this u sub 2 of t is the impulse response of this system, right? So this means that the output, right, should be equal to the input convolved with the impulse response, okay? So you can define u sub 2 of t using this operational definition under convolution, okay? Now these definitions are certainly interrelated because if you look at the second derivative, the second derivative is equal to the derivative of the first derivative, right? So the second derivative is equal to the derivative of the first derivative, okay? So you can write this as x of t convolved with the unit doublet, which gives you the first derivative, and again with another unit doublet, which gives you the second derivative, okay? And we also know that this second derivative can also be expressed directly as the convolution between x of t and u sub 2 of t, okay? So by this formula here, you can sort of see the relation between u1 and u2, right? Because basically u2 is just a convolution of u1 and itself, okay? So hence, u2 of t is just the convolution of u1 and itself. Okay, so if you plot this in terms of a block diagram, right, if you view it in this form, this is like passing x of t through a differentiator that has, this differentiator has impulse response u sub 1 of t, and through another differentiator, okay, to yield the output y of t equal to the second derivative of x, okay? So each one of these differentiators has impulse response u sub 1 of t, but the aggregate of them has a impulse response u sub 2 of t. So this is sort of just a side note to give you a different perspective on how to view these unit impulses, okay? And as an extension of unit impulses, you can also define other singularity functions to, that are defined also under the convolutional operation, right, to reflect its purpose in this system analysis, okay? But we're not going to use a lot of this later on, so I don't want to cover this entire part, but just to give you a couple of examples to see what these functions may be. Okay? So let me end here. So these other parts we're going to skip. Okay. Okay. Oh, okay. So let me clarify a couple of mistakes previously. So yesterday somebody mentioned this to me, and I went back to check the textbook. So there was a typo here, right? So if you look at example 2.10 in the textbook, there should be a negative sign here, okay? But I didn't have that in my notes, okay? So there should be a negative sign here. Otherwise, you would not have, this part of the signal, okay? But in any case, for details of the derivation, please go and look at the textbook. Okay. All right, so do we have any other questions about chapter 2?